Let's begin with some motivation for the Lebesgue outer measure. So let's recall that until now we have seen the concept of elementary measure, the Jordan measurable sets, and the Jordan measure. And its connection with the Riemann integral. So to motivate the Lebesgue outer measure, let's see some examples of sets which are not Jordan measurable. So let's see examples of sets in R which are not Jordan measurable. So one of the easiest examples is to take E to be the rationals inside the interval 0, 1. So this set I claim is not Jordan measurable. Let's see why. So if you consider the inner Jordan measure for this set E, this is going to be 0, because no interval of strictly positive length is a subset of this set E, because it's it only considers the rational points inside 0, 1. So the inner Jordan measure is going to be 0. What about the outer Jordan measure? So the only interval which contains this set E is going to be bigger than 0, 1, and in fact 0, 1, the interval 0, 1 closed interval is the smallest such interval which contains E. So in fact the outer Jordan measure is going to be 1. Therefore we see that the inner Jordan measure is not equal to the outer Jordan measure, and this implies that E is not Jordan measurable. So by connecting it to the Riemann integral, we can also say that equivalently that the indicative function for this set is not Riemann integrable on 0, 1. So this is the standard example of a bounded function on 0, 1 which is not Riemann integrable. Now this example also shows, so I will put this as a remark, it also shows that countable unions of Jordan measurable sets may fail to be Jordan measurable. So here we can take each rational point qk and write this set E that we have as the union, as a countable union of points which are rational numbers. So qk belong to q intersection 0, 1 for all k greater than or equal to 1. Of course, each single rational point is Jordan measurable with Jordan measure 0. This we already know. But in fact it is an elementary set, so it's Jordan measurable. But when we take the countable union of each of these rational points in 0, 1, then it fails to be Jordan measurable. So countable unions of Jordan measurable sets can fail to be Jordan measurable. Similarly, we will see later that countable intersections of Jordan measurable sets may not be Jordan measurable even if they are bounded, So there exist examples of bounded subsets of, let us say, R, which are countable intersections of Jordan measurable sets, but they are not Jordan measurable. So we will see that a modification of the well-known middle third Cantor set will give us such an example, but we will come to that later. So I just put it as a remark for now that countable intersections of Jordan measurable sets can also fail to be Jordan measurable. Another remark is that open bounded sets may not be Jordan measurable. So one example for this is the following. So take an epsilon greater than 0, and you can take the union of these intervals qk minus epsilon by 2 to the power k and qk plus epsilon by 2 to the power k. So this set which depends on epsilon may fail to be Jordan measurable, and we will see the proof later. We will see the proof that this is not Jordan measurable later. Once we have defined the Lebesgue outer measure, it will be easy to prove that this set is not Jordan measurable. Okay, so this last example shows that even open sets may not be Jordan measurable, and this is something that we want to have a nice theory of a measure, so that we are in contact with the topology of the underlying space, and so we would like our measure so that at least the open sets that define the topology on our space, they should be measurable. So in this case this fails. So all these arguments are just to motivate the Lebesgue outer measure, which will take care of all these problems, that countable unions and countable intersections of what we call Lebesgue measurable sets, they will be Lebesgue measurable, and all open sets, whether they are bounded or unbounded, they will also be Lebesgue measurable. So our Lebesgue outer measure will take care of these problems that we face while using the Jordan measure and Jordan measurable sets. So let's see the definition for the Lebesgue outer measure. So let E be a subset of Rd, an arbitrary subset, of Rd. Then the Lebesgue outer measure will denote it by M upper star of E is defined as, so M upper star of E, it is the infimum taken over covering of E by countably many boxes Bi. So Bi are boxes in Rd, and we take the following thing, we take the measure of each Bi and sum it over the whole covering. So we are taking infimum over these values given by the sum of from 1 to infinity, the measure of Bi, where the union of these boxes Bi will cover E. So notice that for the Jordan outer measure, so note that the Jordan outer measure is the infimum of E inside elementary sets B elementary, and we took the elementary measure of B. But now each elementary measure each elementary set can be written as a finite union of Bi, where Bi are boxes in Rd, and you can write the measure, the elementary measure of B as the sum 1 to n m Bi, when we can take disjoint boxes. So Bi disjoint. So we see that the outer Jordan measure, when we use the definition using finite boxes, if we replace this notion of finite boxes by countably infinitely many boxes Bi, and take the infinite sum of all the measures of Bi, then we pass from the outer Jordan measure to the Lebesgue outer measure. So this will allow us to treat countable unions and countable intersections, and as well as open sets in Rd satisfactorily. And from this definition, it is immediate that the Lebesgue outer measure is bounded above by the Jordan outer measure. So we see that the Lebesgue outer measure is bounded above by the Jordan outer measure, but as the following example will show, the Lebesgue outer measure can be much smaller than the Jordan outer measure. So let's take again a similar set than the last set we took for proving giving an example of a non-Jordan measurable set. So here I am taking E to be the rationals in the interval minus R to R. So the outer Jordan measure is, of course, this is going to be 2R, because this is the same as the closure of the set E. The rationals are dense in this interval minus R to R, and when you take the closure, you get the whole interval minus R to R. So the length of the interval is 2R. Now we will try to compute the Lebesgue outer measure for this set. So we know that this is positive because it's only defined using measures of boxes. It's a sum of positive things, so it's always positive. So m star E is always positive. However, if you write, we can write E as the union of these disjoint sets Qk, k from 1 to infinity, Qk belongs to E. So these are rational points within this interval minus R to R. Now each of these can be regarded as a degenerate box, meaning that its length is 0. So the measure of this set Qk, this is equal to 0, and this is a covering of E itself. So m star E is less than or equal to the sum of these sets Qk, k equal to 1 to infinity, because this is a disjoint union, and our m star E was the infimum over all such union of boxes which cover E. So in particular, this union of Qk's is a covering of E by boxes, by degenerate boxes, and so m star E is less than or equal to the sum of the measures of these things, but each one of them is 0, so this sum is 0. So therefore we get that m star E is 0. So here note that the Jordan outer measure can be very large depending on R, capital R. So it can be very large, but the Lebesgue outer measure nevertheless turns out to be 0. To give an alternative proof of the same fact without using degenerate boxes, what we can do, so this is an alternative, I am giving this alternative proof because this technique will be used many times in this course. So this is called the epsilon by 2 to the n or 2 to the k trick, and what we can do here is take for each rational point Qk inside E, we take the interval Qk minus epsilon by 2 to the power k, Qk plus epsilon by 2 to the power k. So this is for an arbitrary epsilon, for an arbitrary epsilon greater than 0. And now the E is a subset of the union of all these intervals Qk minus epsilon by 2 to the power k, Qk plus epsilon by 2 to the power k. So the Lebesgue outer measure is less than or equal to the sum from k to 1 to infinity of these intervals Qk minus epsilon by 2 to the power k and Qk plus epsilon by 2 to the power k. So now we can easily compute what is this measure. This is simply epsilon by 2 to the power k minus 1. So because each term can be explicitly computed, we can now easily compute the sum. This is the sum of epsilon over 2 to the power k minus 1, and this is some constant c times epsilon. Here c is actually half. So since epsilon is arbitrary, since epsilon was arbitrary, we get that m star of E is equal to 0. So this trick of using epsilon over 2 to the power k so that the sum becomes finite is will be used many times in this course, and so it's worthwhile to understand how this is done. Now let's come to some properties of the Lebesgue outer measure. So let E be an arbitrary subset. So here also there is another advantage that E can be unbounded. For the Jordan measurable, for the Jordan outer and inner measures, we restricted ourselves to bounded subsets of RD, but here our subsets can be arbitrary. So another thing that I should mention here is that the Lebesgue outer measure, in the definition of the Lebesgue outer measure, this can take the value plus infinity also. So this value can be plus infinity. So we allow infinite values for our Lebesgue outer measure in order to deal with unbounded sets. For example, if you take the entire RD, then one can show that this value is plus infinity. So we will come to that later, but let's keep in mind that our Lebesgue outer measure can be unbounded and can take the value plus infinity. So now for the properties, if you take E to be an arbitrary subset of RD, then the first property is for the empty set. This says that the Lebesgue outer measure of the empty set phi is equal to 0. The second one is called monotonicity. And it says that if F is a subset of E, then the measure of Lebesgue outer measure of F is less than or equal to the Lebesgue outer measure of E. And the third one is called countable. Let me move to another page. It is called countable subadditivity. So we have seen finite subadditivity, but this one is upgraded to the countable unions of sets. So if E can be written as a countable union of sets En, so En are all subsets of RD, then the measure, the Lebesgue outer measure of E is less than or equal to the sum given by summing up all the Lebesgue outer measures for each En. So here remark is in order. So note that since we are dealing with the possibility that M star E or each of these M star Ens can take the value plus infinity. So we have to define, for example, what is plus infinity and plus infinity, for example, and later on we will also see some factors here, alpha n. So then we have to define what is, if M star E n is plus infinity and alpha n is a real number, then what is the product of such things. So all these are in the structure which is called the extended real number line. So this is denoted usually as R bar, and this is R union 2 points, which is plus infinity and minus infinity. So since we are only dealing with positive numbers, so for the moment we don't need this. This is not needed for the moment. And so we only need to worry about arithmetic operations involving this symbol plus infinity. This is not a real number by definition, but we still need to define arithmetic operations involving plus infinity. So for example, a plus infinity is equal to plus infinity for all a in this R union R plus. So let me write 0 plus infinity open union plus infinity. So we will write this set as 0 plus infinity closed. Similarly, a multiplied by plus infinity is equal to plus infinity for all a in 0 plus infinity, and so on. I'm not going to write out all the axioms, but you get the drift. What we expect to have, if you add a positive number to plus infinity, you are supposed to get plus infinity. If you multiply a positive number with plus infinity, you will also get plus infinity. And there are other rules for division and so on. You can look up these arithmetic operations in any book. And one thing to note here is that cancellation laws do not apply. So for example, if x plus infinity equals y plus infinity, then x may not be equal to y. Because the way we have defined it, both these are plus infinity. So cancellation laws are not applicable always. So we can only apply cancellation when you have finite numbers. So we have to keep in mind these conventions for arithmetic in extended real number line. So let's quickly prove these properties. So for the first one, I will leave the second one as an exercise. This is an exercise, and I will only prove first and third. So for the first one, let's see the proof. So we can write phi as a subset of any real number or any point in Rd, and because this singleton set has measure 0, this implies this is a covering by a degenerate box. So we already knew that m star of phi is positive, but now on the right hand side also this is 0. So this implies that m star of phi is 0. And now for the third one. So here we had E, a union of countably many subsets of Rd, and we had to prove that the Lebesgue outer measure of E is less than or equal to the sum from n equal to 1 to infinity m star of En. First, let's suppose that at least one of these Ens, suppose that at least one En is such that the Lebesgue outer measure of En is plus infinity. Then the above inequality holds by our conventions, by our axioms of the extended real numbers. Then m star E is always less than or equal to this sum from n equal to 1 to infinity m star En, because the right hand side is going to be plus infinity, and we use the fact that any real number x, including any extended real number x, is less than or equal to plus infinity for all x in 0 plus infinity closed. So including plus infinity, we are imposing a partial order, rather a complete order on this extended real number line which stipulates that any real number is less than or equal to plus infinity, including plus infinity itself. So, if at least one of the m star ens is plus infinity, then this inequality is satisfied by our conventions for the extended real line. So, we suppose then that, suppose now that m star en is finite for all n. So, then given epsilon greater than 0, we can find for each n greater than or equal to 1 a collection of boxes, countable collection b n m from 1 to infinity. So, for each n, this is for each n, so we are fixing n and covering, taking a cover of boxes which cover en, that cover en. So, this means that en is a subset of this union m from 1 to infinity b n m, and not only that it covers this en, we also want to use the infimum property. So, we want to use that m star, this sum from m to from 1 to infinity, m star of b n m, rather m, there are too many m's. So, let me write k instead of m for the indices k, b n k's, and this is less than or equal to, we want it to be close to the infimum value, plus epsilon over 2 to the power n. So, again we are going to use the epsilon over 2 to the power n trick, because in the end we want to sum on both sides, and so we want to use epsilon over 2 to the power n rather than just epsilon. So, now we take, so we have chosen for each n greater than or equal to 1 this collection b n k, such that this inequality is satisfied for each n. So, this is for all n greater than or equal to 1. Now, take the collection union n equal to 1 to infinity union b n k, k equal to 1 to infinity. So, this collection is rather this take the union, this is a superset of E. So, it covers E, and this is a countable collection of boxes. So, m star of E is bounded above by this double sum n equal to 1 to infinity, k equal to 1 to infinity measure of b n k. So, this double sum one can take the inner sum and use the inequality that we have. So, we get n equal to 1 to infinity and then m star E n plus epsilon by 2 to the power n, and this last sum is equal to n equal to 1 to infinity m star E n plus epsilon. So, on the left hand side we have this Lebesgue outer measure of E, and on the right hand side we have the sum of all these En's, Lebesgue outer measures of En's plus an arbitrary constant epsilon. So since epsilon is arbitrary, we get the result. Since epsilon was arbitrary, we get the result that we wanted. So these three properties are together known as the outer measure axioms. Outer measure axioms. When we are going to study abstract measure spaces, then we will model an abstract outer measure on an abstract space with these outer measure axioms. And so the Lebesgue outer measure is the prototypical example of an abstract outer measure. Note that the Jordan outer measure is not an outer measure with respect to these axioms, because this countable subadditivity is not satisfied by the Jordan outer measure, because it only satisfies finite subadditivity. So in that sense, even though we are using the term Jordan outer measure, it will not be an outer measure in the abstract sense when we define the concept of outer measures on abstract measure spaces.